Is it true that every relation that is both symmetric and transitive must also be reflexive? Let's try to understand the problem first. What we'll do, we will consider an example. So let us suppose we have a set A. So let A be a set containing the elements A, comma, B. And it is defined and R be a relation, and R be a relation defined on the set A. Defined on set A. And we are defining R as the ordered pair A, comma A and another ordered pair B, comma B. Clearly, our relationship R, thus R is symmetric in nature. This is symmetric in nature because it follows from the definition of symmetry. That means for any ordered pair A, comma A belonging to the relation R, what we have to do, we have to flip the position of the elements within the ordered pair. Now that's also going to give us A, comma A. So A, comma A belongs to R as well. And if we consider the other ordered pair B, comma B, B, comma B belonging to R, flipping the position of the elements within the ordered pair, that's going to give us B, comma B, which also belongs to the relation R. Now that means R is symmetric in our case. Okay, then we can also say that R is transitive in nature. R is transitive. So transitivity property, if we remember the definition, it states that for two ordered pairs A, comma B belonging to the relation R and B, comma C belonging to the relation R, it must imply that A, comma C must belong to the relation R. Now here we have to be very careful. So here the second element of the first ordered pair and the first element of the second ordered pair, they must match. So in our case we have B, only then we can say that A, comma C, that the ordered pair which is the odd, such that we can say that the ordered pair A, comma C is going to belong to the relation R. Then R is going to be transitive in nature. So here what we can say here, we have the ordered pair A, comma A. Now we cannot pick up B, comma B because the second element of the first ordered pair and the first element of the second ordered pair does not match. However, what we can do, we can pick up A belonging to R and we can pick up that same ordered pair A, comma A belonging to R. And of course, it's a trivial way to say that A, comma A must belong to the relation R. Same thing can be done for the ordered pair B, comma. So for this particular relation, we can see that R is symmetric and transitive. And here, of course, here we can immediately say if it is symmetric and transitive, then R is going to be reflexive as well. R is reflexive. Now why is R reflexive? Here R is reflexive because we, for all values of A belonging to the set A, we have the ordered pair A, comma A belonging to R. That is the definition of the definition for relation to be reflexive. That means for all A, that means if we pick up the element A belonging to the set A, this implies that A, comma A belongs to the relation R. If we pick up that element B from that set A, then B, comma B must also belong to that same relation R. So this tells us that R is reflexive provided R is symmetric and R is transitive for this particular example. But our question here is it always true that every relation that is symmetric and transitive must be reflexive? So let's look for a case where this is not true. Okay, so let's say we have, let A, comma B be an ordered pair that belongs to the relation R with a condition that A not equals to B. Fine. So here we are putting a condition. We are putting a restriction here that A and B are not equal. Let us now verify whether if the relation R is symmetric or not. So here, what does it mean? So A, comma B belonging to R. So this simply implies that we have A not equal to B. That's the condition that we have put. If A is not equals to B, can we not say that B is also not equals to A? It means exactly the same thing. But the moment we write B not equals to A, this is simply means we are saying that B, comma A, the ordered pair, which belongs to the relation R with the condition that B does not belongs to A. So this tells us that our relation R is symmetric in nature. This is symmetric in nature. Fine. Okay. Now let's take two more ordered pairs. So we have A, comma B belonging to the relation R and B comma C belonging to the relation R with a condition that we are again putting some restriction here that A does not belongs to B and B does not belongs to C as well. Now, reflexivity states that if we have A comma B belonging to R and B comma C belonging to R, so that's what we are saying, that A does not belongs to B and B does not belongs to C. So if A does not belongs to B and B does not belongs to C, can we not say that A also does not belongs to the element C? So here, if A does not belongs to C, it is simply fulfilling the criterion that A comma C is an element of the relation R, because R demands that the elements within the ordered pair are not equals to each other. That means in our case, if we say A comma C belongs to R, simply means that A cannot be equals to C. So that means here in this case, we are also getting that R is transitive. So R is transitive in nature. Fine. Okay. However, there's a problem here. So R is symmetric and transitive, but R cannot be reflexive here. R is not reflexive. Why is it not reflexive? R is not reflexive. What does it mean when we say that R is reflexive? It simply means that for some, let's say for some arbitrary element A belonging to the set A, the set A is the set on which R is defined, such that A comma A must belong to the relation R. Now, from the definition of the relation, we have already mentioned that the elements of the ordered pair must not be equals to each other. So that means A comma A belonging to R simply means that A does not belongs to A. But how is this possible? How can an element cannot be equal to itself? So that's a contradiction. So this can be only possible if R is not reflexive. In other words, R is not a reflexive relation. So we have to be a little bit careful with this with this statement that every relation that is both symmetric and transitive must also be reflexive. So it's not necessarily true that if they're both symmetric and transitive, that a given relation is also reflexive. So there are special cases, so we have to take care of those cases. So if R is symmetric and transitive, it's not necessarily true that it is reflexive. It could be not reflexive as well.